Good afternoon, everyone. My name is Abhimanyu Kataria, and today we'll be studying about MapReduce. MapReduce is a programming model for the Hadoop ecosystem. It relies on Yarn to schedule and execute parallel processing over the distributed file blocks in HDFS. There are several tools that use MapReduce model to provide a higher level of interface to other programming models. Hive has an SQL-like interface that adds capabilities that help with relational data modeling, and Pig is a high-level data flow language that adds capabilities that help with process map modeling. Traditional parallel programming requires expertise on a number of computing and system concepts. For example, synchronization mechanisms like locks, semaphores, and monitors are essential, and incorrectly using them can either crash your system or program or severely impact performance. This high learning curve makes it difficult. It is also error-prone since our code can run on hundreds or thousands of nodes, each having many cores, and any problem related to these parallel processes needs to be handled by our parallel program. The MapReduce programming model greatly simplifies running code in parallel since we don't have to deal with any of these issues. Instead, we only need to create a map and reduce tasks, and we don't have to worry about multiple threads, synchronization, or concurrency issues. So what is MapReduce? Map and reduce are two concepts based on functional programming where the output function is based solely on the input. Just like in mathematical function, f of x equals to y depends on x. We provide a function or operation for map and reduce, and the runtime executes it over the data. For map, the operation is applied on each data element, and in reduce, the operation summarizes each element in some manner. An example using map and reduce will make these concepts more clear. Hello World is a traditional first program we code when we start to when we start learning programming languages. The first program to learn or hello world of MapReduce is often word count. Word count reads one or more text files and counts the number of occurrences of each word in these files. The output will be a text file with the list of words and their occurrence frequencies in the input data. Let's examine each step of word count. For simplification, we're assuming we have one big file as an input. Before word count runs, the input file is stored in HDFS. As we know, HDFS partitions the blocks across multiple nodes in the cluster. In this case, the four partitions labeled A, B, C, and D. The first step in MapReduce is to run a map operation on each node. As the input partitions are read from HDFS, map is called for each line in the input. Let's look at the first lines of input partitions A and B and start counting the words. The first line in the partition on node A says my apple is red and my rose is blue. Similarly, the first line on partition B says you are the apple of my eye. Let's now see what happens in the first map node for partition A. Map creates a value for each word on the line containing the word as the key and 1 as the value. In this example, the word apple is read from the line in partition A. Map produces a key value of apple, 1. Similarly, the word my is seen on the first line of A twice, so the key values of my, 1 are created. Note that map goes to each node containing a data block for the file instead of moving the data to the map. This is moving computation to data. Let's now see what the same map operation generates for partition B. Since each word only happens to occur once, a list of all words with one key value pairing gets generated. Next, All the key values that were output from the map are sorted based on their key and the key values. The key values with the same word are moved or shuffled to the same node. To simplify this figure, each node only has a single word, which are denoted by these orange boxes. But in general, a node will have many different words, just like our example from the two lines in A and B partitions. Here, we see that U and Apple are assigned to the first node. The word is to the second node, and the words rose and red to the third. Although, for simplicity, we drew 4 map nodes and 3 shuffle nodes, the number of nodes can be extended as much as application demands. Next, the reduce operation executes on these nodes to add values for key value pairs with the same keys. For example, apple comma 1 and another apple comma 1 becomes apple comma 2. The result of reduce is a single key pair for each word that was read in the input file. The key is the word and the value is the number of occurrences. If we look back to our word count example, we see there were 3 distinct steps, namely the map step, the shuffle and sort step, and the reduce step. Although word count is a pretty simple example, it represents a large number of applications to which these 3 steps can be applied in order to achieve data parallel scalability. For example, now that we have seen the word count application, we can consider changing the word count algorithm to index all the URLs by words after a web crawl. This means instead of pointing to a number, these keys would refer to URLs. After the map with this new function, which is called a user-defined function, the output of shuffle and sort would look like this. Now, when we reduce the URLs, all the URLs that mention Apple would look like this. This is, in fact, one of the ways a search engine like Google or Microsoft Bing works. So now, if somebody came to the interface built for this application to search for the word Apple and entered Apple, it would be easy to get all the URLs as the word itself. The first MapReduce paper was actually produced by Google. We just saw how MapReduce can be used in search engines in addition to counting the words of documents. Although it's possible to add to many more applications, let's stop here for a general discussion on how the points of data parallelism can be used in search in this 3-step pattern. There is definitely parallelization during the map step. This parallelization is over the input as each partition gets processed one line at a time. To achieve this type of data parallelism, we must decide on the data granularity of each parallel competition. In this case, it will be a line. We also see parallel grouping of data in the shuffle and sort phase. This time, the parallelization is over the intermediate products, that is, the individual key value pairs. And after the grouping of the intermediate products, the reduce step gets parallelized to construct one output file. You would have probably noticed that the data get reduced to a smaller set at each step. This overview gives us an idea of what kind of tasks that MapReduce is good for. While MapReduce excels at independent batch tasks similar to our applications, there are certain kinds of tasks that we would not want to use for MapReduce for. For example, first would be if our data is frequently changing. MapReduce is slow since it reads the entire input data set each time. Second, the MapReduce model requires that maps and reduces execute independently of each other. This greatly simplifies our jobs as a designer, since we do not have to deal with synchronization issues. However, it means that computations that do not have dependencies cannot be expressed with MapReduce. And finally, MapReduce does not return any results until the entire process is finished. It must read the entire input dataset. This makes it quite unsuitable for interactive applications where the results must be presented to the user very quickly, expecting a return from the user. As a summary, MapReduce hides complexities of parallel programming and greatly simplifies building parallel applications. Many types of tasks suitable for MapReduce include search engine page ranking and topic mapping. Thank you.